Okay, good. So in this lecture, we move on to the public key world. Right? So what we're going to do is I'm going to define the learning with errors problem, both the what's called the decision and the search versions of this problem. And again, as before in the case of SIS, there is a search. There's a worst case to average case reduction for this problem. Right? And this, for a change, I'm not going to show. This is a fairly technical, probably like a 2-hour, lecture by itself. So I'll show you the statement of this reduction, but not the proof. And then we'll go on to sort of building crypto systems based on LWE. I'll show you a construction of. I'll give you 2 for the price of 1. Okay, so I'll give you 2 public key crypto systems based on LWE. Regif's encryption scheme is the first, and I'll show another encryption scheme which is called the dual Regif encryption scheme, also based on LWE. And the security of both these schemes, all the public key crypto systems based on the LWE, actually rely on the hardness of decision LWE. Okay, so which also I'll define. But there's a search version and there's a decision version. The decision version is actually easier than the search version. And the final thing we do to prove security is that we connect the search version and the decision version of the problem. We show that they are actually equivalent. If you can solve one, you can solve the other. Okay. And finally, I will talk about some very, very recent work on improving the efficiency of these systems using what's called the ring LWE, variant of this LWE problem. And what is interesting about this ring LWE is that it gives you 2 birds in a shot. Okay? The first, it improves the efficiency of all these systems. And the second, it actually lets you achieve better functionality. So it lets you construct what's called a homomorphic encryption scheme. Okay, I'll define all these things, and I'll construct this encryption scheme. And these slides, in fact, the slides in the previous lecture, some of the slides are courtesy of Vadim Lubashevsky. Okay, so let's jump into the problem. Learning with errors. I'm going to use it to construct a public encryption scheme. Okay, so what is the learning with errors problem? Imagine that you have a box which contains a secret within it. The secret is an n-dimensional vector in ZQ to the n. Okay? And the box has a big, huge red button on it. What you can do with any button, you can press the button. Right? And what it gives you is the following. It picks a random vector AI. It computes the inner product of AI with S and adds a small error EI. Okay? So EI is a number, is a small number in ZQ. So if you think of ZQ as Q is 257, E is in the interval plus minus 8. Okay, it's a very small number relative to Q. Okay, so this is what I get. I press a button, I get this sample. Okay, A1 is a vector, and the number B1, which is the inner product plus noise. Okay, so there is no restriction there is no requirement that I press this button once. I do this again and again and again and again. For a polynomial number of times, I get many samples of this form. Okay, every time this vector AI is chosen uniformly at random, independently, and I get an inner product plus an independently chosen noise, which is a small number. Okay, so this is what I get from this box. And what does the problem ask me to do? It asks me to find the secret S. Okay, I can press this button many, many times, get many samples, collect them. Can I now find the secret contained within this device? S. Okay, so that's the search version of the search version of the LWE problem. Okay, so let's think about this for a bit. Okay, so what is this problem? Right. So assume for a moment that the box gave you the inner products without the noise. Okay, what can you say about the hardness of this problem? I get many inner products of the same secret with many vectors. It's easy. Yes? Good. That's because I get many linear equations in the same secret. Eventually you have an n-dimensional secret. I'll get more than n equations, and I do Gaussian elimination. Same as before, the problem is easy. So what makes this problem hard is the fact that I don't get linear equations. I only get noisy linear equations. Linear equations plus this arrow term, noisy equations. Okay, and so this is the LWE. This is the learning with errors or LWE problem. One can define sort of a decisional version of this problem. So this is a search version. It says, I get all these things, find the secret S. Okay? I can also define a decisional version of this problem, which says, given, so let's imagine that you are in one of two worlds, the left world or the right world. In the left world, the oracle gives you, LWE samples as before. In the right world, I get uniformly random numbers. Okay, A1 is uniformly random vector, B1 is random. It has nothing to do with the secret S. Right? So it just spits out random numbers. The question is, can I distinguish between these two worlds? So this is like a Turing test, right? I mean, I get samples from either left or right. You have to distinguish. You have to tell which world you're in. Okay, so this is the decisional version of the LWE problem. Okay, so what can you say about, right off the bat, what can you say about the relation between the search and the decision problem? Well, if you can solve the search problem, then you can clearly solve the decision problem, right? You assume that you're in this world, you try to reconstruct the secret, and check that you actually reconstructed the secret, because you can recompute this in a product and check that it's small. Okay, so the decision version is actually easier than the search version, and yet what we will show it's actually as hard as the search version. So this is a non-trivial. So what is trivial is search implies decision. What is non-trivial is decision implies search, and that we will show in a little. Okay, so these are the two variants of LWE. And again, we can write it down in a sort of a matrix vector format as before. These are A1 up to AM are the LWE samples, the vectors in the LWE samples. And what I get is the inner product of the AI with S plus a little noise here. So that's what I'll call B. Okay, so this is what I get from the LWE oracle is the AIs together with the B. Okay, so note that this is kind of the problem is kind of the dual to the SIS problem, and one way to see it is that this matrix is tall and skinny, whereas the SIS matrix was fat and short. Okay, so this is how you write the LWE problem. A matrix times a vector plus noise. That's what I'll call B, and distinguish this from random. Okay, so this problem is it's a very natural problem when you think about it from sort of many angles, right? So the one natural way to interpret this problem is saying that I give you many noisy linear equations. The inner product is a linear equation, but I give you a noisy linear equation. Find a solution. Right? So that's the obvious way to interpret this this problem. The other way to interpret this problem is saying is the following. It's from the perspective of coding theory, right? So think of A as a random error correcting code. What is an error correcting code? It's an object that takes a small message and maps it onto a larger code word. Okay? What LWE does is it computes this code word, takes this message S, constructs the code word which is A times S, and adds a little bit of noise to this code word. So the LWE problem is saying, I give you a noisy code word, can you decode it? Can you find the message S? So that's exactly. It's a problem of decoding random linear codes because A is random. Okay? There are many ways of thinking about, many equivalent ways of thinking about this problem. Okay, so as before, you can show a worst case to average case connection for this problem in the sense that there is a polynomial time. Forget about quantum for a minute. It's a polynomial time reduction that takes as input any n-dimensional lattice, as before. It has an oracle that solves the LWE problem, namely It takes LWE samples and gives me back the secret. Okay, it solves LWE, where the error is chosen. So far, I didn't say anything about the error in the LWE problem. It could be anything as long as it's small, right? That's all I said. What this reduction says is if you choose this error from a special, very special distribution, namely a Gaussian, a discrete Gaussian distribution over Z cube, then you can produce, the reduction produces as output an approximate solution to the same problem, the shortest integer vectors, the shortest independent vectors problem. Okay, so what this says is, if you can solve LWE with these parameters in dimension n with modulus q, where the error is chosen from a standard deviation sigma, you can solve, you can produce you can produce lattice vectors with length roughly n times q over sigma. Okay, so what does this mean? What does all these numbers mean? Right, n, q, and sigma. What do these mean? Right? So note that the smaller the error in the LWE, the easier it is to break, the easier it is to solve. In fact, if the error is 0, it's trivial to solve. The error becomes bigger and bigger. In fact, if the error is uniformly random in Q, then you really get uniformly random numbers, and there's no way you can, there's no solution even. Right? So the smaller the error, the easier the LWE instance. Therefore, if the oracle that I get solves LWE for a smaller error, using this reduction, I get a bad approximation to it. So this oracle does less work than an LWE oracle which solves for larger error. Right? So as a result, I can only get a worse approximation to SIVP. Okay? Smaller error, less powerful, I can do less with it. Okay, so that's the one.
What do you think if we replace Gaussian distribution with the other?
Okay, that's a good point. That's what Michel and I were talking about over the break. We don't know. It's a good question. It's a very good question.
It comes from the theorem, previous theorem, like uniform Gaussian, adding Gaussian distribution gives.
Not quite. I mean, it comes for a different. It comes for. They're not completely unrelated. I mean, the Gaussian distribution comes up for related reasons, but it's not the same reason as the smoothing lamp. I mean, it comes up for a different reason.
This theorem does not use smoothing them.
Smoothing them at all. At all. Yeah. Yeah, that's right. Okay, so what are the reasonable parameter settings for this theorem? I can set Q to be a polynomial modulus, and sigma to be a 1 over polynomial times. So I can set Q to be n to the 100 if I want, and sigma to be n to the 99, okay, or n to the 50 if you want. Okay, so that will give me a polynomial approximation to the shortest integer vectors, which is presumably hard, right? So the best approximation algorithm for SIVP that we know is what we saw yesterday from the LLL algorithm, which is 2 to the n approximation. Okay, so any polynomial approximation is supposed to be hard, and I can potentially assume make that as an assumption.
Potentially or provably?
No. I mean, we can't prove anything of this sort, right? Because I can't prove that any of these problems are hard, because if I did, P not equals NP.
Okay, so,
right.
So is it NP hard?
No, it's not even NP hard. So if you do show that this problem, this problem that I can build, crypto systems out of is NP hard, it's a big achievement. So the question, central question in cryptography is, can I base the hardness of cryptographic systems on NP hardness? Okay? So can I construct a one-way function whose hardness is based on the NP hardness of some problem? We don't know. We have no clue. It's a huge open question. Okay. So it's not NP hard, but it is hard. I mean, in the sense that many people have tried it, for the same reason that factoring is believed to be hard. Many people have tried it, smart people, and they couldn't break it. Therefore, it's okay. That's the best we can say about all of cryptography, essentially.
So SVP is NP-hard, but
SVP is NP-hard, but approximate SVP is not NP-hard. Okay, so let me actually. This is an interesting point that you're raising. Let me take that as a detour. So what is the hardness of? What can we say about the hardness of SVP or even SIVP for different approximation values, right? So one can draw this line. So this is one. So this is one SVP, which is really the exact SVP. Right? So this is known to be NP-hard. In fact, we can push this NP-hardness a little bit beyond exact SVP. So we can show that polylog n approximating the shortest vector is also NP-hard. Okay, so this we can show. On the other hand, so the other end of the spectrum is polynomial time algorithms, right? So this is so 2 to the n over 2 approximating SVP is in polynomial time in P. And we can push this a little bit also to get 2 to the n over log n approximation in polynomial time. Okay, so there's a huge gap between the two. So where does cryptography lie in this picture? Right? What is the approximation factor that you get out of applications to cryptography? And that actually lies smack in the middle of the two. Okay. So this is the NP-hard world. This is the polynomial time world. And for cryptography, we need to assume, so far as we know, something like order of n, hardness of order of n approximating short vector. So polylog n is NP-hard. Order of n, we have no idea. It's not known to be NP-hard. In fact, we have evidence to suggest that it is not NP-hard. So if it is NP-hard, then all these complexity classes, and some of these complexity classes collapse, which we don't believe to be true. So it's likely not NP-hard. On the other hand, it's very far from polynomial time also. So it's a safe assumption to make as far as we know. Right? So that's so in fact, if you think about it, the approximation factor that you get from here is at least as big as n, right? So it cannot be, it's n times a positive number, never bigger than 1. Okay, so that's what. So it's not NP. So all these systems are not based on NP hardness, but still, they're hard for the same reason that factoring is believed to be hard. Okay. So there's a little detail that I left out, which is that this reduction is quantum. In the sense that if you have an algorithm that solves LWE, what you get is a quantum algorithm that computes approximate short vectors, and that is still believed to be. So in fact, for all these lattice problems, quantum algorithm, you don't know how to do any better with quantum algorithms than with classical algorithms. In other words, the best approximation factor that you can get for shortest vectors using quantum algorithms is 2 to the n over log n. No better than classical algorithms. Okay? So this is still a meaningful theorem if you assume that SVP is hard for quantum algorithms.
Without considering quantum computer, there is reduction.
There is a reduction. Yes.
And then even with quantum computer, we don't have better reduction, right?
We don't have a better algorithm.
A better algorithm.
Better algorithm for lattices, yes.
So without quantum, this is true. Correct? True? Polynomial time reduction?
Is it true or not? So that's a question. Okay, yes, it is true. And that's what Vaikuntanathan shows. He says, okay, let me take this reduction, let me sort of remove quantum from the picture. Okay? So he says there's a classical, there's no quantum. Quantum, why quantum, right? I mean, it's bizarre. So he says, okay, let's make this a classical reduction. Okay, so in other words, if you can solve LWE, you get a classical polynomial time algorithm that computes this approximation, which is believed to be hard. Well, a classical reduction gives you both reductions get an algorithm that solves LWE, right? A classical algorithm that solves LWE. And a quantum reduction produces a quantum algorithm that computes a shortest vector. Okay? So if you invoke the quantum theorem, you get a quantum algorithm that solves the shortest vector. Okay? Not an algorithm that you can implement, but there exists a quantum algorithm. Okay? A classical algorithm gives you, it doesn't talk about quantum stuff at all, quantum weirdness at all. It's just a classical algorithm. That's it. Okay?
Oracle is classical algorithm.
Oracle is a classical. So
All algorithms.
yes, the oracles. So what's bizarre about this quantum reduction is that even if the oracle is classical, you will get only a quantum algorithm. Okay, and so it doesn't matter actually if the oracle is classical or quantum. You'll always get a quantum algorithm. So that's what Chris says. Okay, well, classical. Okay, so that's the worst case to average case theorem. So remember that, so one thing to note about this worst case to average case theorem is that it talks about search, the search version of everything. In other words, what it says is that if you can solve the search version, then you can solve various problems in the worst case. But when you build a crypto systems, as you will see, the hardness of these encryption schemes, the crypto systems that we build relies on the decisional version of the learning with errors problem. Okay, so if you can break these crypto systems, you end up solving decisional LWE. If you solve search LWE, then you end up solving all these worst case problems. But there is a gap between the two, right? If you can solve the decisional LWE, you can solve search LWE. In fact, it turns out that you can, and we will prove this. Yes. Well, you see, when we build crypto systems, okay, we will use LWE. Okay, LWE is an average case problem, right? Because what does it say? I give you a random A and A in a product with S for a random S. It's hard to solve. Okay, so it talks about distribution. It's an average case problem. The thing about average case problems is that they are necessary for cryptography, right? I mean, because cryptography says right? So what if I give you an encryption scheme, which is hard to break for one public key, but easy to break for all other public keys? Okay, will you buy? I mean, here's an algorithm. Can you give me $1,000 for it? You won't, right? Because who knows what this public key is, right? So what we want in cryptography is an encryption scheme, for example, which is hard to break for most public keys. It's hard on the average, right? On the other hand, what people study in algorithms are worst case problems. Okay, so when I study the hardness of shortest vector, the LLL algorithm that we constructed, it doesn't talk about average case at all. It talks about the worst case hardness of shortest vector. So what would be nice is if you connected between the average case and worst case, right? If you can solve a theorem which shows that if you can solve the average case problem, then you can solve the harder worst case problem. So that would be a great theorem to have, because that connects algorithms to cryptography, right? Randomly selected. Why? Because it's a random matrix and random vector. It is worst case. Exactly. Precisely. Well, and that's the reduction. That's the magic of the reduction, right? So a reduction says how to take any SIVP, any basis, any lattice, and construct a short vector for it using an oracle to an average case solver. Okay, so it's not obvious by any means. There is magic in this reduction. I'm not going to tell you about this magic.
So the magic
is to connect between the worst case and average case. Yes. Magic is in the proof. Unfortunately, you won't see the magic today. Okay, so, but you see the point of the theorem, right? I mean, forget about the proof. What it says is that you can go ahead, you can safely build your crypto systems based on LWE, and they will be hard, assuming that there is a lattice for which it is hard to find the shortest vectors, which is a very safe assumption to make. Okay, so this is the worst case established case theorem. And we can also show a search to decision reduction. Okay, good. So that, let's construct a public encryption scheme based on the hardness of LWE. Okay, so from this point on, forget about SIVP, forget about worst case. We'll only talk about LWE. In fact, this is what you should do if you want to construct crypto systems based on lattices. You should forget about, I advocate forgetting about lattices, working only with SIS or LWE. Okay, that's the cleanest way to do cryptography from lattices. Okay, so what is this public encryption scheme? It's a scheme due to Rage from 2005. And how this works is the following. Okay? So the secret key for the encryption scheme is a vector S in ZQ to the n. Right? So this is the LWE. It's like the LWE vector. And the public key is a matrix A together with A times S plus E. Okay, so this is like the LWE samples. Secret key is the LWE vector. Public key is LWE sample. So what does the hardness of search LWE say? It says that given the public key, it's hard to find the secret key. Right? So it's obvious. It's plain. How do you use the secret key and public key to the public key to encrypt? I'm going to show how to encrypt a single bit. Okay? So if you want to encrypt multiple bits, you encrypt the first bit, you encrypt the second bit, and so on and so forth. There are more efficient ways of doing it, but for simplicity, let's look at one bit. Okay? So how do you do this? Well, you pick a random R in 0, 1 to the m. So each coefficient is small. My ciphertext is going to be R times A. Okay, so R is in n dimensions. So it makes sense, syntactically makes sense to multiply R with A. Right? And I'm going to also compute R in a product with B and add my message to it. So in fact, I won't add the message by itself. I will multiply the message with Q over 2. Q over 2 is not an integer, so I'm going to round it. So this bracket means rounding. Okay, so you can think of this as computing R times A and R in a product with B. And I'm going to either add Q over 2 to it if the bit is 1, or I'm not going to do anything to it if the bit is 0. Right? It's either 0 times Q over 2 or 1 times Q over 2.
Q is even?
Say that again?
Q is even?
No, Q is not even. So that's why I said, this is this bracket means round, Q is closest to Q. In fact, Q is not even. So Q is just an integer. In fact, let me think about it. Q is prime. Okay, so it depends on what the LWE problem is hard for. So the LWE problem, when it comes to you, it comes bundled with a Q, comes bundled with an error distribution, and so on and so forth. So it depends on the hardness of LWE. You can choose Q to be not a prime, but safest to let Q be a prime. Okay, so for now, think of Q as a prime, a small prime. Okay, so it's not in number theory. You talk about 160-bit numbers, right? So 2 to the 160. That's not the kind of Q that we are talking about. We're talking about 257. Q equals 257. Okay, 8 bits rather than 160 bits. Okay, it's a very small prime. So we can think of another way to think about this is that the hardness of number theoretic problems, they come from the fact that these numbers are large, right? So 160 for LT curves, 1024 for RSA, and so on and so forth. Here, for lattice problems, for LWE, the hardness doesn't come from the how large the modulus is. It comes from the fact that the dimension is large, n is large. That's where the hardness comes from. Okay, so in any case, the ciphertext is R times A, R in the product with B, plus I add the message times the rounded Q over 2. Okay. Pictorially, it's R times A, R times B, plus Z times 2. Okay. Same thing. Okay, so that's great. how do you decrypt this? Right. So this is your cipher. This is the encryption of message Z, message bit Z. How do you decrypt this? Okay. So again, the ciphertext is UV. The U is R times A and V is R times B plus the message. Okay. So to decrypt it, I have the secret key. Right. So when I decrypt it, I have the secret key. I'm gonna compute U in a product with S minus V. Okay, so what is U? U is R times A. What is U in a product with S? It's R times A times S. Okay, so this is all well defined because the dimensions match up nicely, and R times A times S is a number. Okay, it's a number in ZQ. And then I'm going to subtract the number B from it, which is R times B plus Z times Q over 2. But what is B? B is simply A times S plus E. Right? That's the way we define the public key. So it's R times A times S minus this quantity. R times approximately A times S, right? A times S plus noise plus the message. Okay. Let's do a little bit of algebra, right? There's R times A times S here. There is R times A times S here. Minus. So that cancels out. What you're left with is this in a product minus R times E plus the message. Message times Q over 2. Okay. So now we look at this quantity. We compute this quantity. We look at it. We say, okay, R is small, right? Because it's a 0-1 vector, and E is small because it's the LWE error. Right? So both are small. And therefore, their inner product is also more or less small. It's going to grow by a little bit, but it's still going to be fairly small. Okay. So then I say, well, if Z is 0, what is this number going to look like? So this is 0. Okay. And the number is going to be R in a product with E, which is small, as we just saw. So this number is close to 0. It's small or close to 0. And when I say close to 0, I actually mean so we're talking about ZQ, right? So it's think of ZQ as kind of a sort of circular, what do I call it? Think of Q as 257. Okay, 5 is close to 0, and so is 252. Okay, it's close to 0 from the other direction. Okay, so that's what I mean by close. If Z is 1, this number is going to look like Q over 2, more or less Q over 2, minus a small number, plus minus a small number, right? And that is, close to Q over 2, because this number is very small. So I look at this, how do I decrypt? Again, I compute this number, which I can do using the secret key. I look at it and say, is it close to 0, or is it close to Q over 2? If it's close to 0, then the encrypted bit is 0. Otherwise, the encrypted bit is 1. Okay, so that's that. Okay? We good? Okay, so that's for correctness. Why is the scheme secure at all, right? I'm going to show a very strong statement of security, which says that the ciphertext, even if I give you the public key, the ciphertext of any message, 0 or 1, looks random to you. Okay, without the secret key, just given the public key, the ciphertext looks totally random. So therefore, it contains no information on the message. Okay, so this gives us what's called the in-CPA security or semantic security, just correctly. Okay, so why is it secure again? Right? So first of all, I'm going to assume the hardness of decisional LWE, which says that this number B, this vector B, which is computed as A times S plus E, actually looks random to you. Okay, so that's what decisional LWE is. This is a whole bunch of LWE samples that I just stacked up. That is going to look like it's totally random to you. Okay, so in other words, I can replace AB by a random matrix and a random vector, nothing to do with S. Okay, so now imagine for a moment that R is actually, the vector R that you use in encryption is actually random in ZQ to the M. So it actually isn't random in ZQ to the M, it's actually, it consists of small coefficients, right? Plus, minus, 0, 1 coefficients. So imagine for a moment that it is actually random. Then what you get is R times A and R times B would actually be random, and therefore this whole thing doesn't contain any information on the message. Okay, that's what we want to say. But the point is that R is not uniformly random in ZQ to the n. It's only uniformly random in this small space, in 0, 1 to the n. Okay, so it's not totally random, but it's not totally deterministic either, right? So it has some entropy, and I'm choosing it from some distribution which has some entropy. So how do you make use of this fact? And the way to do this is using what's called the leftover hash lemma, which I'm going to state. I'm not going to prove it. What leftover hash lemma says is the following. It says that if you take a matrix A together with B, and this is just a bigger matrix, right? One more column. And then multiply this matrix with a vector R. So this is a uniformly random matrix, right? Because I just switched B from being LWE to uniformly random. This is a uniformly random matrix. And I have a vector multiplied by this uniformly random matrix. Okay? Now, what leftover hash lemma says is that this guy looks like a random matrix and a random vector, a uniformly random vector, as long as the vector R has enough entropy. Okay, so I didn't choose R. R is not uniformly random in ZQ to the m. It has 0, 1 coefficients. It has entropy. But what this lemma says is that if R has sufficient amount of entropy, then this guy, this is really the public key together with the ciphertext, looks uniformly random. Okay. What do I mean by sufficient entropy? I want the entropy of R. I can apply this lemma if the entropy of R, which is equal to m, right? It's a uniformly random 0, 1 vector, is bigger than the output length of this function, namely the bit length of R times AB. Okay, so you can think of this lemma as saying that I'm going to take a vector R which has some entropy, it's not uniformly random, and I'm going to extract uniformly random bits from it. Okay, so it's a randomness extraction lemma. And of course, I cannot create randomness out of nothing. So I have to have enough entropy to account for the output length. Okay, so that's the output length is n plus 1 times log q, because the length of this vector is n plus 1. Okay, but this I can set. M and n and q are totally up to my liking, right? So I can set m to be larger than this number, and then I can apply this lemma. When I apply this lemma, what happens? I'm going to switch these two matrices, which was R times A before and R times B before, to uniformly random matrices. Okay, nothing to do with R, nothing to do with anything. Totally uniformly random matrices. Okay, now I'm done. Why? Because my public key looks like random matrices, and my ciphertext looks like random matrices and vectors plus the message. But random vector plus the message is a random vector. It has no information about the message. Right? So we're done. Okay, this is the proof of security. The proof of security shows that under the decisional LWE assumption, the ciphertext looks uniformly random. In other words, it contains no information on the message. Okay, so bottom line, this is the encryption scheme. All the algorithms in one page. Secret key, public key, encrypting, and decrypting. So all these operations are simple linear operations. You're just adding or multiplying small numbers, right? So the basic operations of the system are actually very fast. And this is it's a relatively efficient crypto system. We will see one drawback of this system in a little bit, maybe in the next lecture, and we'll see how to remedy it. Okay, but this is a priori, this is a very sort of nice, very efficient crypto system.
Excuse me.
Yes.
Previous slide.
Yes.
What do you mean by random? It's not uniform distribution.
It's a uniform distribution.
And it proves only uniform distribution.
Yes. Yes, and that's all I need, right? Because if this vector u is uniformly random in ZQ, right? I'm going to add some number to it, either q over 2 or 0. but you won't be able to tell which is which, because I take a number and I add a random number, you get a random number indifferently, right? So that's exactly what I want. Precisely what I want.
Even with some structural.
Even with the structure of the message, it doesn't matter what the message is, right? It's random. So that's yes. Yes. So it's a good question. Maybe I should have said here that I should pick R randomly in this set. So R is a random, so each coefficient of R is either 0 or 1, probably half, right? Probably half it's 0, probably half it's 1, right? So that's how I pick R. So now what is the entropy of such an R? So each coefficient of R has entropy 1 bit, right? I mean it's like half 0, half 1 bit. So the total entropy of R is m bits. Right, so that's exactly what I use, in fact, in this case. The entropy of R is m. And if I set this m to be, so what is m here? M is the height of this matrix. If I set it to be tall enough, then I get security. Okay. And in fact, what does the height of this matrix mean? Remember that I constructed this matrix by taking many LWE samples. In fact, each row of this matrix is a new LWE sample. Right. So what this means is that if I get it's hard to solve LWE if I get more than n log q, roughly n log q samples. Okay, so that's what it means, and that's okay. I mean, in fact, if LWE assumption says that even if you get a polynomial number, any polynomial number of samples, it's still hard. So clearly, if I get this many samples, it's hard. We'll see in a minute. So this system by itself, I would say, is really practical, and that's because the operations of the system are actually very simple. Right? It's just adding and multiplying small numbers, 8-bit numbers, essentially. But the point is that the public key, which is a big matrix, so the public key is an n by m matrix, right? Each of whose entries are drawn from CQ. What is n and m? N is roughly 128, let's say. M is bigger than n log q. Therefore, it's more like 4,000. If you set q to be 257. Good. Excellent question. So far in the system, So far in the system, you just encrypted 1 bit, and the length of your ciphertext is n plus 1 elements in ZQ. Right? Well, what you can do is you can actually encrypt many bits with essentially the same ciphertext. And the idea is the following. Okay? So why do you lose efficiency when you encrypt many bits? There are 2 reasons why that happens. One is that even if you forget about r times a is a vector and this is a number, right? So the big part of the ciphertext is in fact r times a. But let's forget about it for a minute. What I'm doing is that to encrypt 1 bit, I have a log q bit ciphertext. Okay, so I'm packing 1 bit into a log q bits. That's fairly inefficient. What I can do is I can pack many bits into just this one ciphertext. Okay? And that's because think of z as not 1 bit, 0 or 1. Think of it as, let's say, a number from 0 to 8, right? So 0, 1, 2, 3, up to 7. To encrypt it, what I'm going to do is I'm going to multiply it by q over 8. Instead of q over 2, I'm going to do q over 8. Then the same argument carries over, because when you decrypt, you're going to get a number which is close to a multiple of q over 8, and that tells you what the encrypted bit is. Okay, so that gives you, you can pack many bits you can pack actually order of log q bits into the log q bit ciphertext. We're not done, because really the elephant in the room, the big deal here is this vector r times a, right? And that's n log q bits. It's a huge vector. The second thing I can show, which is not quite as straightforward, is that I can encrypt many bits while reusing the same R times A. Okay. So let's say I want to encrypt a huge number of bits. What I can do is I can use the same R times A, and I can sort of keep changing this second quantity. Okay, so I'm reusing this numbers many times. So overall, amortized, I can get a constant, right? In the sense that to encrypt n bits, to encrypt k bits, I can have a ciphertext of length 2 times k if you want. Okay, so that I can make very, very efficient, very tight. What is the bigger problem is really the length of the public key. Okay? So the public key is an n by m matrix. If n is 256 and m is 4000, it really is a pretty huge matrix. That also you can solve, it turns out, and we'll talk about it later. So that's. So I think. So do you think you want to stop and continue with the next lecture, because it's kind of self-contained at this point? Okay. All right. So that's that.